Well, thanks for hanging in there until the bitter end. um, I, I, earlier you saw the remote control. I brought that here, so because the stuff that we are talking about now is more in this camp. Okay, HDF troubleshooting. I think the main message, forget about all the details, and we will see how much I can show you live, is you should definitely try to follow a certain methodology as you approach performance problems. And that starts with learning whatever is relevant about your environment, learning about what your platform is available, allegedly capable of doing in terms of throughput, so that you have some realistic expectations about the kind of throughput, for example, that you want to achieve. And then you user instrumentation is good, so putting in a few printfs here and there, or doing timings and so forth is great, but I think ultimately you will come to the point where you say, I just need some tools that sort of quickly give me information that guide me, that help me to understand where are these problems coming from, more about their nature, and then give you some clues about what, by addressing what, you might hope to improve your performance, and then at the same time also understand when the information provided by a tool doesn't really tell you anything about your performance problem, and you have to look elsewhere, and really sort of trying to get the right tools under your belt. And my opinion is there are three that definitely should be there. The GPerf tools, the Google performance tools, as they used to be called, Darshan, which is sort of a nice sort of performance performance profiler, and then ultimately a tool called Recorder that gives you sort of more timing information, conflicts, sort of data hazards, read after write, write after read, and those three tools, and I'm going to cover them here. So important thing is just try to make those three tools part of your toolbox, and then I hope everything will be a lot easier, at least in 80% of the cases. And one way to illustrate that, and again, the source code for all of this is in the GitHub repo. If you look into HDF5 troubleshooting, the code is here, the PDF that I'm showing you right now is here, and then there are a few scripts that we come back to later. And the problem sort of illustrating these tools is actually done maybe best if the problem that you are trying to diagnose is not too complicated, the application is not too complicated. It shouldn't be a sort of a total toy problem either, so it should have some relevance to your work. And a very nice problem is actually part of the Hdfio IO test suite that is not completely synthetic and fantasy. That's a common problem, but it's also not so complicated that you have to sort of spend a lot of time getting your head around what the application is doing. What the simple test application is doing is basically over time, in each time step, or sort of synthetic time or physical time, it doesn't really matter, you are writing multiple two-dimensional arrays. So time step 0, you're writing, in this particular case, 500 two-dimensional arrays, and each of these two-dimensional arrays is 100 by 200 double precision floating point numbers. And you are doing this, if you have n ranks, you assume that you can factor them so that there is a number of process rows and a number of process columns. And then you can think about, well, this could be weak or strong scaling in a sense where either you fix the total size of the array. So in that case, the total amount of data written and read would not depend on the number of processes, But in the case when you do weak scaling, you keep the per process load of reading and writing constant, and that's both are very interesting scenarios. And so if I write that in some kind of a pseudo loop, you could say, well, okay, for each time step, for each of these arrays, I'm going to write a bunch of these arrays, depending on if it's strong or weak, and then I'm writing or reading as it goes. And just for specificity, here are some numbers that they actually use in the Hdfio test. Simple enough. Now, of course, there is a lot of missing information here. You might sort of jump the gun and say, oh yeah, I know how to do that. Just make two-dimensional arrays in groups and so forth, and then off you go, and that's fine. There's nothing wrong with that. But if you take a step back, again, HDF is sort of this thing that has a lot of knobs and buttons and dials and so forth. There are many different ways how you could do that, depending on additional constraints. For example, we said, okay, in each time step, we want to write a bunch of arrays, and well, the first thing could be you could stack them together. So instead of writing two-dimensional arrays and many of them, you could pack them together, for example, in a three-dimensional array. And take that one notch up, you could actually stack all these three-dimensional arrays together in a four-dimensional array. So there are already, as you can see, a lot of different possibilities and combinations here. Of course, not all of them can be done in all circumstances. So for example, if the size of these two-dimensional arrays were variable, you didn't know how many time steps you do or how many arrays you are writing for time steps, you have to then make different choices about the layout and the storage layout and so forth. But hey, that's what all these buttons and knobs and so forth on that remote control are for. And then the question is, sometimes the data is written in a different way than it is read back. And so then you have to either find a compromise or sort of find some kind of a sweet spot. And for HDF5, as you all know, you can do things contiguously chunked. If the data is compressible, you might prefer to do that. What's the target file system and so forth. And then we just heard a lot about sort of collective versus independent IO and so forth. So there are just, if you want to characterize these as problem dimensions, there are many problem dimensions here that you could explore. So in the sample code that's included in the repository, we look at sort of 24 basic combinations. So 24 is the magic number that you will see a few times. First of all, this idea of the different griddings. Are we writing two-dimensional data sets? Are we writing three-dimensional data sets? And then you can think about, well, how are the dimensions of these ordered? Is it time first and then arrays and then X and Y, or is it array first and then time and then X and Y? It depends. That may vary from case to case. And in this case, we just look at contiguous or chunk layout and collective or independent. So if you take this, we have 6 griddings, 2 layouts, 2 MPI modes. That's 6 times 4, that's 24. Okay. And it doesn't stop there, but these are the ones that sort of that come to mind right away. Okay, so just a quick sort of back of the envelope calculation in a sort of weak scaling scenario, and that's the only one that we are looking here. So if you want to double the number again, you could say, okay, I'm going to do this weak scaling, strong scaling. We are writing 500 by 100 times 200 times 8, so roughly 80 megabytes per step, and we are doing 20 time steps, so we would be writing 160, 1.6 gigabytes, roughly on a single process. If we scale that up, then we write 4 times that, for example. And you could go out and do some user instrumentation. That's where you would usually start, and measure the time. How much time do you spend creating these data sets, whichever way you decide to go with the 2D, 3D, 4D. And then how much time you spend reading and writing, and throughput might be your metric where you want to see, well, how fast can I write, how fast can I read, and so forth. And at some point I might try, I'll show you how to compile this and run this and so forth. What we'll find is when you take these 24 parameter combinations, in an ideal world, they would all be the same. It would really just be a matter of logic or opinion, whether you structure it this way or that way. It doesn't really matter for the program execution time. Unfortunately, that's not exactly how computers work. Here are, and I'm going to try to explain it slowly. This is sort of my legend here in the upper left-hand corner. This is a single process run. So up here, I try to indicate the spacing of the process grid. So 1 by 1, that's a single process. And the y-axis is execution time in seconds. And then the x-axis, there I sort of align my 24 runs, 24 combinations. So there are 24 bars. And what I've done is I've arranged them so that the first group of 8 corresponds to writing 2-dimensional arrays. The second group of 8 corresponds to writing 3-dimensional arrays. And then the last group corresponds to writing 4-dimensional arrays. And among those groups, there are subgroups here. As we said, you can then look at, am I doing chunked or am I doing contiguous layout? And it turns out that the group of the first 4 is the contiguous layout, and the group of the second 4 corresponds to chunked layout. And so in terms of bar height, high bar means bad. We are spending a lot of time. You can read that as wall time if you wish. And then it's broken out into yellow, that's the reads, red is the writes, and then blue is the creation time. So high bar bad, low bar good, if throughput or execution time is your metric. Okay, and then what I've done is I've surrounded this sort of 1 by 1 reference run with 1 by 4, so 1 process row, 4 process column, or 4 process rows, 1 process column, or then sort of a square arrangement 2 by 2. And of course, you can scale that out any way you want. Long story short, there is quite a bit of variability here if you look at just the numbers on the y-axis. So it can be as low as below 4 and as high as above slightly 10. And then similarly in the other things. So what's going on here? Why is that happening? And of course, visualization is very important with all these tools. This is just a simple spreadsheet sort of put together based on user instrumentation. But one thing that stands out already here is to see, well, wait a minute, there is a lot of blue here, and it looks like it's sort of in the chunked camp, where there is quite a bit of creation overhead. So we want to keep that in mind and think about that. And that's actually true regardless of process grid and so forth. So that's what I would call, in optimization terms, a low-hanging fruit, that at least even if you can't do anything about it immediately, just to think about what would cause that, or why is that. And then I just threw in a slide here because unfortunately on the cluster, the X redirection didn't work, so I cannot show you the Google performance tools as visualized through Kcachegrind. I'm sure many of you on your workstation, you have a tool called Kcachegrind installed, where you can just take these prof files, these traces generated, for example, by the Google performance tools, and just load them into Kcachegrind, and then or Qcachegrind for Qt based variant, And then you can sort of see how much time you're spending in the different functions, and then sort of a sample-based call graph like this one. And here I've taken just 2 samples, again, 24 combinations. So I just picked run number 8 and run number 17. And in this outline view here, you see that's sort of the call graph based on samples. And topologically, for example, these 2 call graphs are different. So there's definitely a difference between run 8 and run 17, regardless of time and whatnot. It's just that the distribution of the time samples across these different activities is very different. So there's definitely something going on here. And this information is important. Even in some cases, especially if there are intermediate layers, let's say there's a Python wrapper around this or something like that, you'll be amazed sometimes where you are spending your time. So even before thinking about and say, oh, I know what's going on, it's just this and that, and I'm going to tweak that a little bit and so forth. Take the time, run the gperf tools, create a trace, look at the call graph. If it makes sense to you, great. Then it just confirms your expectation. But I find myself most of the time that the call graph doesn't look anything like what I expect. So it's definitely worth doing before you go on a wild goose chase. And then I'll come back to Darshan in a moment, but let's see if I can show you something on the cluster here. Oh, let's see, can I log in? Yes, I can log in. It's still there. So if you go into tutorial, into HDF5 troubleshooting, right, this is what's here. There is a configure script. I got already a make file, but I'm going to do the configure again. So if you do configure --help, it will show you that you will have to specify, well, a destination, specify, we'll come back to Darshan in a moment as one of the profiling tools. You have to tell this configure script where the Google performance tools are and where the HDF5 library is. So in good old spec fashion, we just load what we need. So we load HDF5. Oh, okay, so here we have to be a little more specific because we've got two versions of this. So let's just make it this way. Then we will load the gperf tools. Oh, if I could spell. Yes, tools. And finally, we need to load the Darshan runtime. Spark. Okay, and so now that's a little bit, now you might say, well, I can use something like autoconf and so forth that finds these paths, and in an abstract way, that's also true. Here, unfortunately, I have to do it a little bit in a kludgy way. I have to find out if I ask, well, where is whatever libdarshan.so, for example. I have to look at I have to ask spec to tell me where it's located, and you see it's mount spec, opt spec, Linux Ubuntu compiler name and so forth, but then it has sort of this obscure thing back here. I'm going to do the same for HDF5, and it's going to give me 2. And finally for the gperf tools, and that's what I'm going to feed to configure. So I'm going to say then configure -- prefix, and I'm going to just install it in the local directory. I'm going to say Darshan path equals, and then I'm going to use this path, and then I'm going to say gperf tools equals let's see, and last but not least, HDF5, what was the argument? yeah, I think, oh, with HDF5. Oh, I'm sorry, I just screwed up. I think it's with Darshan, not Darshan. And then, was it with GPro? Yeah, with, and finally, I think it was, yeah, with HDF5, and we are going with this one. Okay, and so then you just, I guess I have to make do a make clean, then you just make, and that compiles this, and you're good to go. So if you go to the bin directory, also, so this is old stuff from earlier. It's interesting that it's still there. I'm gonna run. So this is that, yeah. And there are a few scripts in there. One that I'm not going to run right now because then I might send the cluster south again. This is a typical script to assess the performance. So if you have published specs or technical data, you can compare that. But here, what you want to measure is, for example, how quickly, at what rate can you write a 100 gigabyte file with a 1 megabyte block size, and then you would do the same thing with 4 kilobyte blocks for read and write, and that sort of gives you a rough idea of what your environment is capable of doing. And yeah, then you are ready. So the first thing you can do is, I'm going to run it just on a single process. So you do Hdfio test, and if you run that, it's going to echo, it's reading from a configuration file called Hdfio test. Well, you can specify the name on the command line, but the default is Hdf5io test ini. And it specifies things like, okay, we are doing 20 steps, 500 arrays, 100 this, that. Scaling is weak, okay, that's irrelevant in a single process run. But the slowest changing dimension is step. We are writing to a 4-dimensional array. We are laying it out contiguously in the file. And again, okay, for a single process run, the independent MPI/IO is irrelevant. But here you see sort of the typical user instrumentation back out, so to, output, so to speak, where you print the wall clock, you print the file size, and then of course for multiple MPI ranks, you want to see the min and max, and of course for a single process, there's not much to see here, but you see that we are writing at sort of about 100 megabytes per second, and we are reading at about 200 megabytes per second with OS caching and whatnot, but that's pretty respectable. Okay, so and then of course you can scale this out. So if I just show you the contents of that ini file, it looks like that, like any ini file. And in order to modify these parameters, you would just at the bottom of this add sort of a user section where you override the defaults that you want to override. And for our favorite 24 combinations, I've done that for you already. Let me just make sure that this is actually not running anything. So there is a script called combinator.shell. Yeah, this doesn't do anything. So if you run that combinator, it just creates sort of all these ini files. Okay, in this case, it would be not interesting. You would typically specify a process topology, like let's say the 2x2. So if I look, for example, then at run1 .ini, it would say, hey, okay, this is the default section, but here the combinator would say, okay, 2 process rows, 2 process columns. We are writing a 2-dimensional data set. Step is the slowest changing dimension. Contiguous layout, independent I/O. The output HDF5 file is this, and then it will write records to a CSV file so that later we can then easily, for example, create spreadsheets as like the one that I showed you. So you can just compile that and run that. I'm not going to do that right now because I'm running against the clock here. What else is here? Well, I mentioned Darshan already. So the first tool of which I showed you a visual, that slide, is really gperf tools. And I think there is a script in here if you want to know how to do that. Is there a question? Sorry. I thought somebody said something, but okay. So here's the same script with running the gperf tools, where you basically in the make file, it links against the libprofiler library, and then by specifying these environment variables here about the sampling frequency, the output file where you want to put that profile data, it knows that it has to load the profiler SO shared library. And then you just use this Google pprof tool to create callgrind compatible output. And then that's what you load into kcachegrind. And then you create sort of the figures that I showed you earlier. If you load the preprof profile, those are the kinds of pictures that you get. And then you can sort these things and click on things to drill down on that call graph and so forth. Okay, good. I want to focus now on Darshan. Darshan is another one. And here is the sort of the profile. You basically run this by running sort of your MPI job just as you would usually. The only difference is that you LD preload libdarshan.so. And remember, in this spec environment here, we said we had to do this a little bit in a kludgy way. We would look at the Darshan libdarshan.so as part of the so-called Darshan runtime, and so that library is actually located in this directory. So you would LD preload it. Well, it's actually in /lib in there, I would imagine. Yes, here we go. Okay, and then you run that, and maybe we should run, I'm going to run this right now, because that creates a Darshan output file where then you can either use some of the visualization and post-processing tools that the Darshan folks provide for you to create some summary data, and I'll show you some. Or as of the current sort of master branch of Darshan, there's actually a very nice Python module so that you can load this Darshan sort of profile and then use all the beautiful visualization tools that you have available in Python to really extract the performance counters that you are interested in. So let's just run this maybe. So in this case, all I would do is I would say, oh, I have to do one more thing, which is I have to specify where I want to write my Darshan profile. And on a cluster, there's typically a default path where all these Darshan profiles get placed. In this case, when Stephen built this, he sort of compiled it so that we can specify an invariant environment variable called Darshan, I believe it was Darshan profile path. So I'm just going to set that to my home directory, for example. And then I can just say, yeah, LD preload, and then there's a little bit of a sermon here, libdarshan.so, and then I'm just going to run Hdf5 IO test.ini. It's just going to be a single process run, but that's cool. And let's see what that will run a few seconds, and then that will hopefully create a Darshan output file. If not, we will, okay, that's interesting. Oh, lookup fed Darshan, I think I got the environment very wrong. I think it's Darshan log path, because this segfault comes from, if you ever see something like that, you're running Darshan and it looks like your application is doing fine. The reason is, in the default path, Darshan typically, on a cluster especially, it bakes in the Slurm job ID and things like that, but ultimately it places it into a directory that's the date, that's today's date, so that's today's date. And I think the name of the environment variable was actually Darshan log path, not Darshan profile path. So let's try this once more. And then if that is sort of clean, then that means we get our Darshan profile and we can take a quick peek at that. And then you will get sort of a sense of what the type of information that's, oh yeah, good. Okay, so that was clean. So now I have to load another spec module, because Darshan is sort of split into two parts. One is the Darshan runtime that we've seen already, and the other part are these so-called Darshan utilities. So let's load those. And then there are tools such as, you can say, since this, oh, well, first let's look at the, at our home directory. So here's our Darshan output file. And yeah, it creates sort of this weird name that there's typically a job ID in there, and then some kind of hash. And so I wouldn't get hung up. And that's really depending on how your system administrator decided to configure this output name, but we're not going to sort of lose any sleep over that right now. But then you can run a tool, for example, there is Darshan parser, and then just pass that name here, and then we're going to do a pipe less. And then you see, you get information Darshan collects for you. It tells you at the time when you ran the job, what were the file systems that were mounted. And then you get these are called performance counters. So POSIX bytes, POSIX max byte, consecutive reads and writes, and so forth. And so there are these counters, so that would be that. But then the first, if you wish, the prefix of some of these counters, this is what in Darshan they call a module. So in this case, I think there is an overview. Darshan supports a variety of modules. It supports POSIX, it supports MPI-IO, it supports certain HDF5 calls. And then you can sort of go through this list and, for example, look at IO operations that you did. So, for example, I'm looking here for POSIX read. Maybe it lumped these together under MPI reads. Here are the axes and sizes. So, for example, here we see that using MPI-IO, for example, in the range of 100 kilobyte to 1 megabyte, we did 10,000 reads, for example. And now you can go back to your back of the envelope calculation and say, well, what would that be? Did I really do 10,000 reads in that size range? And this area, sort of where you get, visually, you can think of that like a histogram, where you get this type of information. That is typically a good first sanity check, because I think, as Quincy mentioned earlier, for example, if you see a lot of tiny, like in this range, 0 to 100 bytes or 100 to 1 kilobyte reads or writes, and you see tens of thousands or hundreds of thousands of them, those are the early signs of trouble, and you better understand first where are they coming from, and eliminating those in some cases might be 80% of solving your problem if you can identify where they are coming from, or it could be a bug in your program or something like that. But this is the type of information that Darshan gives you also for standard IO, but in this case, there are just some operations because we are writing this type of information here to the console. That's where that comes from. But if you use the, there's, for example, a Darshan summary Perl script, for example, that will actually create PDF files for that. Unfortunately, I have to admit that I forgot to ask Stephen to install LaTeX on this cluster node. You need, in a Darshan installation, to create these pictures, you need, I think, yeah, you need GraphViz and LaTeX and so forth. So unfortunately, I cannot create that file for you. But here you see, this is, for example, we looked at the performance counters for reads and writes, where it sort of breaks these out into ranges. This is the visualization of these counters, and you get sort of a multi-page, Darshan creates sort of a multi-page summary for you here. Okay, moving on. There's one more tool that you should have under your belt, which is Recorder. And Recorder is installed in Spec. And I forgot to copy the slide, but let's see what we can do. So I would do a spec load Recorder. And this is a nice tool. There's a repository on GitHub by Chen Wang. Here we go. You should check that out. It's on GitHub, but it's also part of SAC. So if you do a spec install, a spec build, then it's there. And it gives you also, he calls it multi-level information, so related to POSIX.io, to MPI.io, to HDF5 and so forth. But it also gives you sort of resolved in time. It gives you information resolved in time. So as you can see, for example, from these figures here, it tells you, for example, which ranks write at certain offsets in a file, but you can also get that sorted by time. So over time, are your writes or reads, for example, monotonically increasing in terms of offsets in the file, or are you constantly seeking around and jumping left and right and all over the place, which is typically not good for performance. And it compiles this nice report for you. Again, I have a little script in here called recorder.shell. It's the same kind of affair. You just LD preload librecorder.so, and then you run your program as you would usually, and then there is a Python script that that just generates the report that then contains figures like that. So let's maybe run that. So I have to look at where Recorder is installed. So spec recorder. So it's here. So we would do an LD preload equal this, and then lib recorder.so, and then we would just run Hdf5 test. Oh, and something is going on here. Do I have this? Maybe do I have to run this with oh, maybe you run this with, oh yeah, no, oh, no such file. Oh, librecorder, there's no librecorder. Oh, there's librecorder.so. No such file or directory. Let's see. Maybe let's try maybe an S1 and for Hdfio test, and then something like, I believe, run one.ini. Oh, no, it's lib recorder, no such file or directory. I'm a little lost here.
If I may get.
Yeah.
I could look into this one, so I installed the LaTeX for you and the GraphViz.
Oh, okay, thanks. Well, let's.
Did you mention what LaTeX you want? I picked the TTEC.
I think that should be fine if I do Darshan Analyzer and then just take my Darshan file here. Okay. Now let's see which. Or is it Darshan? Oh, Darshan job somewhere. I think that's what it is. Till then. Okay. It says Linux Ubuntu. Oh, do I have to? I mean, it's calling the. Oh, you mean it needs a Perl LaTeX module. Yeah.
So, just for, I'm going to dump something onto your screen, okay?
Okay.
In the lib recorder is in the user local lib. I'm not sure if you're looking for a specific one.
No, just anyone should be fine.
Just any of them? Okay,
yeah,
just a second.
Yeah, I mean, I can try running this one again. So you said it's in user local. Okay.
ETS.
User local lib, lib recorder. Now it's kind of frozen. I don't know if I. Oh.
Yeah, that was.
Recorder. .so. Very good. HDF5. I don't know. I have run this before, but I don't know.
This is okay. You have instructions, so people can find.
Yeah. You have instructions, and yeah. So what's in the script here works. Yeah. Maybe long story short, as I said in the beginning. It is important that you know what your system is capable of doing, that you have kind of a performance back of the envelope calculation of what to expect. And then, yeah, look at these three tools, gperf tools, Darshan, Recorder, look at the output. If you can explain the output, the good news is if you have all three, you can sort of cross-match them, because if one of them makes sense to you, but not the others, then maybe it doesn't make as much sense as you think it does. and it's then interesting to sort of, once you believe you see something, then to make the connection and say, well, if that's the case, I should be seeing this in this other tool. And yeah, if that all adds up, then that's good news, and that's where you want to be. And in tough cases, all these three tools will not help you to get where you want to be or where you think you can be, but then at least you are equipped with some numbers that tell you something, and then you have to look into tracing tools like the newer generation, the linear tools on your cluster installation, or Tau, or something along those. But then you have to work much harder. Whereas these, I mean, as I was able, I hope to convince you, you can run these in a few minutes and just do a quick sanity check, and that already gives you a lot of information. Rather than going out of your way. And what's important is also you need a system, and that's why I personally find these cloud-based environments so attractive, is they are low noise compared to a busy cluster environment. The performance changes with the weather, or even more often than the weather. Well, that's true in California for sure. But yeah, on a busy system, you may get very volatile sort of performance data. Whereas, at least from my limited experience with cloud-based environments, the performance tends to be rather consistent if you can get the instances and you stick with an instance type or an instance type class. You get pretty consistent and reproducible results. I mean, that's of course very important. And that's maybe where I'm going to leave it. So yeah, use the right tools, and rather than, it's really, I mean, it's happened to me so many times, and I'm sure to some of you, is you think you have the explanation and you work with that assumption without having verified it, and then you pay for that dearly, because you go off on wild goose chases. Your explanations get more and more complicated, and at some point you just have to apply Occam's razor and say this is getting out of hand, and then you go back to square one and you run a tool like that, and then you look at the output and you say, duh. Anyway, thanks.
Okay, thank you, Gerd. Questions, please. It was a long day.
Yeah. And I think what we are also, I don't know if we have a survey form, but I think we would like to know what people, how they felt about this format, modulo the technical glitches, but that's, yeah, I don't know if that's any harder now than it used to be, but it's certainly, I think, considering this was sort of one of our first attempts, it went actually pretty well. But
some of us had access to cluster, lucky ones.
The lucky ones, the chosen ones. Is it possible that I would look at those charts, because this cluster came out fresh the oven, that I personally didn't have the time to take a look, and I would be interested to take a look at that. The one that where you have the red graph.
You mean right, was it in the PDF?
It was in the latest slides, I believe.
Oh, or maybe it was in the recorder in GitHub.
It's the recorder.
Yeah, it's this one.
Yeah.
Yeah.
The one in the middle.
Yeah.
Top
so
middle.
This is from Chen Wang's webpage. So he just took. This is not from my application. This is from one of his.
Mm-hmm.
Yeah.
Okay.
Yeah. But this is the kind of information that you get there. So which is quite a bit. So and you get that breakdown by rank and by time, which is sort of important to have that. And then also, yeah, this information of where are you writing in the file. And then sometimes, yeah, you see patterns like this and you ask yourself, well, what is going on here?
So after you ran this application, then you would be able to generate these
yes,
graphs.
by running this, yes. So by running this Python script here, so as you saw, you just LD preload, you just LD preload the library, and that creates sort of the recorder files, and then you run this Python script here. So and by the way, all these pictures and so forth, he put some nice web controls in there, so you can pan and zoom on them, because sometimes you have very fine patterns, but the controls, and then he creates this recorder report. It's just an HTML file, and you can just open that in any browser, and it's very well done.
Yeah, there is another question. Do you have any common performance problems to share with HDF5 usage specifically?
Yeah. No, it's just, I mean, it goes back to sort of what I keep harping on, this remote, too many buttons, and in some cases, let's be honest, I didn't know from the very beginning what all these buttons do. Sometimes, some of them I just looked at and I thought, I'm not sure what that button is about. And then of course there are library defaults, and unfortunately, either you don't know what the library defaults are, and then they may not be what you think they are, even if you knew that they were there. And yeah, and going back to sort of the earlier discussion about the ecosystem and higher level interfaces and so forth, I mean, these guys do a pretty good job to sort of anticipate and try to steer you away from the worst mistakes. But if you read, for example, this our HDF5 practical tips article, you will see that there's only so much they can do, because at the end of the day, they have to do what your script, what your program says to do, and it's at some point you have to stop guessing and you just have to do stuff, and it may not perform. And but yeah, I think sometimes, for example, as this is not specific to HDF5, but as we saw earlier, I alluded to sort of this bluish stuff in the PDF. I think I've closed it already, the creation. That has to do, for example, with, well, yeah, creating a data set really means more than just creating the data set. It also means that, like the difference between malloc and calloc, that you initialize, in the case of calloc, the memory with 0. And that's just common, that's not specific to HDF5, but there is an extra cost sometimes noticeable, between just grabbing a chunk of memory and really initializing it. And the bluish stuff, actually, there is a macro in the code where you can just turn on and off the initialization or the population of chunks with fill values. And when you disable that, you say, I'm overriding my chunks anyway, no need to initialize them. The blue pretty much goes away. So sometimes it's little things like that, but then, yeah, to make the association, or to be able to identify this is the little knob or the little switch that I have to turn, that can be hard. And so maybe unfortunately, there is no magic bullet.
Thank you.